Good evening, all of you. Is my voice clear? And the video also to everyone? Thank you. So, any doubts on the previous class to anybody? Please tell. I think we are discussing a problem in the end, and we concluded that, right? A small context there, isn't it? So, I just give the idea. That's very simple. I have finished it, but I have a small doubt at the end. Then I have clarified this. So, there we have taken that f of AB, f of A, f. This is one hierarchy. Second hierarchy we have taken like this. So the claim of the problem is f of AB over f is equal to mn, where m is nothing but f of A over f and n is nothing but f of B over f, and also given that m and n are relatively prime, GCD of mn is equal to 1. This is the thing actually we have in the problem. Am I correct? Please check the data. Now, to prove this thing, there we have concluded in the first place that this value is dividing this. So how we have proved? From this hierarchy, if you calculate the dimension f of AB over f, this is nothing but f of AB over f of A into f of A over f. So this equal to, this value stands as it is and this is m. So from this we have taken that m divides f of AB over f, because this value is nothing but a multiple of m. Accepted? With the same argument, using the second hierarchy, from the first hierarchy you have taken that m divides this value. Using the second hierarchy, using the same technique, we say that n divides f of AB over f. Since the two numbers are dividing this value, the product will also divide the same value. Therefore, mn divides f of AB over f. It means that it is a divisor of this value. So we can say one thing, that mn value is less than or equal to the dimension. Accept all? Any doubts? So this is, you take it as the first equation. Now I am going to prove that this value will be less than or equal to mn. That is my intention. Therefore, the claim will be proved automatically. The strategy clear for everyone? Say. Yes, this will happen when GCD of Mn is equal to 1. If it is not 1, then it will be different. Yeah. Now see, f of AB over f of A, we are taking this value as a number, right? So let us take that this value is K. So what does this means? In this hierarchy, whenever you specify the dimension between these two, you are considering the algebraic element. So what is the element different here? B is the element different here. So the dimension here is nothing but the polynomial degree for which B satisfies over this field. Clear? As per the dimension definition is concerned. Any questions? If you specify a dimension, it means that it is the degree of the polynomial satisfied by the field over the other one. So you take that K is the degree of the minimal polynomial satisfied by the element B over the field f of A. Okay? Are you getting it or not? In writing, we can say, let K be the degree of minimal polynomial satisfied by B over f of A. Now, actually, in the problem itself, it is given that f of B over f equal to n. It means that if you calculate the dimension of the vector space, it is n. In other words, B satisfies a polynomial of degree n over f. Please understand, here B satisfies the polynomial over f of A. Here B satisfies the polynomial over f. So if you take that the degree of the minimal polynomial is n, then what could be the relation between the value k and the value n? What could be the relation between k and n? So did you get the idea of what is meant by minimal polynomial? Because let me say, if I have taken a value 2, 2 satisfies so many polynomials, isn't it? So the dimension is defined that the smallest degree polynomial satisfied by particular element. Based on that, the dimension is defined. Clear? If you take a value root 2 satisfies so many polynomials of different degrees. So if you want to calculate the dimension of q of root 2 over q, you should take the smallest degree irreducible polynomial over q satisfied by 2. Here it is nothing but 2, because x squared minus 2 is the smallest degree polynomial satisfied by root 2. If you say that Root 2 satisfies the polynomial x minus root 2, but this value will not belong to the field Q. Clear? Any questions, please? Now see, here I am saying that B satisfies a polynomial of degree n, which is the smallest. Here I am saying that B satisfies a polynomial of degree k, which is smallest. Please understand, the fields are different here. On this field, this is the smallest degree polynomial. On this field, this is the smallest degree polynomial. If you want to get the relation between these two, it is nothing but k less than or equal to n. It is nothing but k less than or equal to n. So why I have taken this relation? Because here you got that f of ab over f is equal to this value into this value. And I have given a number that this is nothing but k. So what you got? This is equal to k into m. So the relation between k and n is k less than or equal to n. So this is less than or equal to m into n. This is equation 2. So in the first equation, you have proved that mn less than or equal to this value. In the second equation, you have proved that this is less than or equal to mn. So from 1 and 2, the claim will hold. That was the idea, right? Now you please take a note of that. First part I have given clarity already in the previous class. Now this part, equation 2 part, you can take a note of that. That was the complete solution of the problem. Any other queries for anybody? Say. Please understand, this is the smallest degree polynomial. This is also smallest degree polynomial. Let me say, if we say that k is greater than n, so then what happens? As we know, n is the smallest degree polynomial satisfied by b. This is another polynomial. So k cannot become the smallest degree polynomial. It will not become the minimal polynomial. Please understand. I give the hierarchy, then you get the understanding. So here, the polynomial is taken here. Say here the degree is n. Here the polynomial is taken here. Here the degree is k. Now k greater than n, then what happens? Right? So, if you say that g is a polynomial taken over this field, please understand, g is a polynomial taken over this field, it means that all the coefficients in g are nothing but the elements in the field f. Yes or no? Right. So, here I am saying that b is satisfying another polynomial over f. Please understand. Don't confuse with this symbol a. You just forget this. Here g is a polynomial taken over f. Here g is also a polynomial taken over f. So a may be involved or may not be. That doesn't matter. A is an additional element compared to F. So basically, the coefficients are taken over F. So here what happens? In F, you are saying that the element B is satisfying two minimal polynomials. One is F, another one is G. As and when you mention minimal, it is the smallest degree polynomial. If you say that K is greater than N, how this will be minimal when compared to N? Did you get the logic? How this will be minimal when compared to N? So let us take small numbers, then you get the idea. Let me say, suppose N is equal to 2. It means that the element B satisfies the polynomial whose degree is 2 and all the coefficients are belonging to F. All coefficients belong to F. So here you are taking K. Let us take K is equal to 4. So here it is also a polynomial where all coefficients belonging to F. Now what happens? You are saying that 4 is the minimal polynomial. Here saying that 2 is the minimal polynomial. Minimal polynomial cannot be 2. It should be always 1. The degree cannot exceed the thing, right? In a short note, if you say that B has minimal polynomial degree 2 means B, the smallest degree polynomial satisfied by B is nothing but 2. Whatever the field you take, whether the field is taken over F or taken over F of A, whatever the case may be, the smallest degree polynomial satisfied by B is nothing but 2. This is the conclusion from the statement F of B over F is equal to N. If K is greater than N, it means that the smallest degree polynomial is 3 satisfied by B. In other words, B cannot satisfy a polynomial of degree less than K. That is the implied idea. It cannot be true, right? Are you getting the thing or not? Let us take a small take. You just understand like this. Minimal means if I say A has minimal polynomial of degree 2, it means that A cannot satisfy a polynomial of degree less than 2. It satisfies the higher degree polynomials. So here if you say that K is greater than N and B satisfies the polynomial of degree K, which is minimal, it means that B is satisfying a polynomial of degree K only. Less than K polynomials will not be satisfied by B. That is the idea here. That is the idea here. At this point, if you take K is equal to 4, it means that B satisfies the polynomials of degree 4 only. Less than degree 4 polynomials cannot be satisfied by B. That is the underlying idea. But this is a contradiction as per the problem taken, right? That's why always K must be less than or equal to N, since the field is different here. Since the field is different here. That's the idea. Now you got it? Right. So that was the conclusion of the problem. Now let us start today's class on splitting fields, which will be very interesting for you. So earlier there are some problems asked on this concept, the concept of splitting field. So I want to mention one thing, that when compared to finite fields or finite extensions or the field extensions, there are a lot of results involved on that. We have time is insufficient and we cannot give guarantee that all these results will be given in the exam? We don't know. So as per the exam point of view, I am taking all the crucial results as well as problems for your preparation. Since everyone is following one standard textbook, whatever the results available based on finite fields or splitting fields or field extensions, you follow them. If you have any doubt with regard to a particular result, you just give me a posting in Telegram to me. I will clarify your doubt how the proof is compiled, right? So we cannot discuss all the proofs with regard to finite extensions because there are so many proofs and results involved on them, right? We don't know. We cannot give guarantee that how many of them will be given straight away in the exam. Clear? There are a lot of results. So I will cover each and every definition, all important results as well as problems with regard to exam point of view. That I will give guarantee. So let us take the concept that splitting fields. So what is meant by a splitting field? Suppose you take a polynomial, f of x belongs to f of x. So for the field f, you consider an extension E. That means f is subfield of the field E. Now, this extension, we call it as splitting field for the polynomial. We call it as splitting field for the polynomial if it satisfies that this polynomial in this field should be represented as product of linear factors. In other words, all the roots of this polynomial are belonging to E. Okay? In other words, you can say that this extension is finitely generated over the roots of this polynomial. So you can say E is equal to f of alpha 1, alpha 2, so on, alpha n, where all these values are nothing but roots of this polynomial f. This is the definition of splitting field. So, for our good understanding, let us take the small example that so q of root 2 is splitting field of q for the polynomial x square minus 2. Here, the coefficients are rational numbers. So, this polynomial belongs to q of x. And we know that it is an irreducible polynomial by default. Now, if you take this is f of x, we can write it as x plus root 2 into x minus root 2. Accepted? Yes or no? So, the roots of this polynomial are nothing but plus root 2 minus root 2. Accepted from the roots itself, plus root 2 and minus root 2. Now, these two roots belonging to this field, accepted or not? Since root 2 belongs to here, we can say that plus root 2 as well as minus root 2 belongs to this. So, over E of x, all these factors belonging to this. In other words, the coefficients or roots in this polynomial belonging to this field. Therefore, q of root 2 is the splitting field of x square minus 2 over q. So, we are calculating the splitting field with respect to a particular polynomial over a particular field. The very word splitting gives that all the roots of that polynomial are belonging to that field. Okay? All the roots of that polynomial are belonging to that field. Clear or not? You take one more example. take R and C. Real number system, the complex number system. Now you take the polynomial x square plus 1 belongs to R of x. We know that this polynomial is irreducible over R because the roots of the polynomial are not there in R. So this polynomial is nothing but can be written as the product of linear factors x minus I into x plus I. So while considering the splitting field, you are representing the polynomial as product of linear factors. So here I is the root and minus I is the root. These two roots belongs to C. So C is splitting field of this polynomial over R. Okay? Does it make sense? See, always the polynomial should be irreducible because if it is reducible, reducible is nothing but having root. So all the roots will be in F itself, right? Isn't it? The concept of irreducible is nothing but there is no root. The concept of reducible is nothing but having roots. That's all. In a simple nutshell, we can say like that. Now, is that clear? The concept of splitting field? Now, there is one good understanding that how many splitting fields will be there. So, whatever the number of splitting fields you consider for a polynomial, they are isomorphic. Let me say, for the polynomial x square minus 2, there are two splitting fields, let us take. Then the two splitting fields or the two extensions are nothing but isomorphic. We can build an isomorphism between these two. Clear? Now let us take the splitting field consideration. Then you know how to calculate the splitting field, and we can say what should be the degree of the splitting field. That we will discuss. So you take the polynomial x cube minus 2 belongs to q of x. So we say that this polynomial is irreducible over q because if you take the prime number p is equal to 2, it satisfies Einstein criteria. For this polynomial, so this is irreducible over q. In particular, if you want to calculate the root of this polynomial, now tell me, if you want to make this value as 0, the value of x cube must be equal to 2. Then this will become 0. Accepted? Yes or no? So from this you can say that x is equal to 2 power 1 by 3, nothing but the cube root of 2. So if you substitute cube root of 2 in place of x, then this will become 0. So this is nothing but the root of this polynomial. Is this value belongs to q? No. So it is always irreducible, right? Are you getting the idea? So 2 power 1 by 3 or cube root of 2 is a root for this polynomial. So if you calculate the dimension q of 2 power 1 by 3 over q, it is nothing but the degree of irreducible polynomial satisfied by 2 power 1 by 3 over q. And what is the polynomial? This is the polynomial x cube minus 2. This polynomial is taken over q. This polynomial is satisfied by 2 power 1 by 3. And this polynomial is irreducible. The degree of the polynomial is nothing but 3. So the dimension here is nothing but 3. Okay? Did you get the idea how I have written 3 there? So again I will repeat. If you mention like this, it means that the element what you have specified here is satisfying a polynomial whose coefficients are exclusively taken over this field Q, and that should be an irreducible polynomial. So you are mentioning the degree as the dimension here. Okay, the degree of the polynomial satisfied by that element you are taking as the dimension there. Clear? Yes or no? Right. Now please understand, if you want to calculate splitting field of this polynomial, splitting field is nothing but whatever the roots are there, you have to know all the roots and you need to identify what is the field which consists of all these roots. That is the interesting thing. Now, from this 2 power 1 by 3, we can say one thing, that x cube minus 2 is nothing but x minus 2 power 1 by 3 into some other polynomial, right? Yes or no? So, I want to know, since it is a third degree polynomial, it must contain 3 roots. The roots may be real roots, irrational roots, complex roots, whatever the case may be. I know one root. It is nothing but 2 power 1 by 3. I want to know the other roots also for this polynomial, because if you want to write the splitting field, you must know all the roots of that polynomial what you have considered. So for x cube minus 2, I must know the root, the remaining 2 roots, what are they? So if you understand that this polynomial is of the form a cube minus b cube, because x cube minus 2 can be written as x cube minus 2 power 1 by 3 whole cube. So applying a cube minus b cube formula, this thing can be written as, so x square plus, you can write it as 2 power 1 by 3 into x plus 2 power 2 by 3. A minus b into a square plus ab plus b square. Accepted? Now, what are the roots of this polynomial? If you know the roots of this polynomial, it means that you have calculated all the roots of this x cube minus 2. I will say that this is a quadratic polynomial. If you apply minus b plus or minus, b square minus 4ac is nothing but negative. So it contains the complex values as roots. It contains the complex values as roots. Since the complex numbers occur in pairs, so the 2 roots of this polynomial are nothing but the complex numbers. So please understand that here I am not calculating the root. I am saying that this polynomial has complex roots. So let us take the root as alpha. Let us take the root as alpha. Right? Now, this is the hierarchy of the fields I am mentioning. The least field is Q, which is in the given problem. The next hierarchy I have taken as 2 power 1 by 3. And the next hierarchy I have taken as 2 power 1 by 3, comma alpha. This alpha is root of this polynomial. Now what happens, if you want to know the dimension of these two, so q of 2 power 1 by 3, comma alpha over q of 2 power 1 by 3. This is nothing but 2, because this alpha is satisfying a polynomial. This is the polynomial. It is irreducible over this q of 2 power 1 by 3, because please understand, the coefficients in this polynomial are nothing but belonging to this. Belonging to this. Right? So, from this, the degree of the polynomial is 2. So, this value is nothing but 2. Now, actually, the splitting field is nothing but the highest field what you have written. Because all the 3 roots of this polynomial are belonging to this field. So this is the splitting field. Now, if you want to calculate the dimension is nothing but how many elements will be there in this basis. So we simply apply the product formula what we know. So q of 2 power 1 by 3 comma alpha over q is equal to q of 2 power 1 by 3 comma alpha over q of 2 power 1 by 3 into q of 2 power 1 by 3 over q. So this is nothing but 2 into 3, 6. That was the answer. How it is written? You are going to know what is the degree of the polynomial here. You have to know what is the degree of the polynomial here. Multiplying these two values, you will get the dimension. That was the underlined idea. Okay. Now please take a note of that. I want to take similar kind of problems again. So how to calculate splitting field, everyone should know. After noting, please inform. Any questions or any doubts for anybody? How it is written? The value at 6 to anyone? Right. So can I take the other problem then? Now I am taking the polynomial x power 4 minus 2 over q of x. So by default, I say that the splitting field of this polynomial is nothing but q of 2 power 1 by 4 comma I. So just like proceeding the previous problem, I want to calculate the splitting field as well as the degree. Now see, if you want to make this value as 0, very simple, x power 4 must be equal to 2. Then only this will become 0. In other words, x is equal to 2 power 1 by 4. Accepted? So, in the first place, if you calculate q of 2 power 1 by 4 over q, this is nothing but degree of irreducible polynomial satisfied by 2 power 1 by 4 over q. Please understand, this is the irreducible polynomial because by Einstein criterion, if you take p is equal to 2, this is the irreducible polynomial over q. So, what is the degree? 4. So, it is nothing but 4. So, the hierarchy is coming like this. This is q. I have taken q of 2 power 1 by 4 here. This is the next hierarchy. So, I am calculating the dimension here. How I am calculating? So, what is the degree of the polynomial satisfied by 2 power 1 by 4 over this q? That is I am actually calculating. So, here the degree is 4 and the polynomial is nothing but x power 4 minus 2. Okay for all? Right. Now, splitting field is nothing but this polynomial contains 4 roots because this is the 4th degree polynomial. So, all these 4 roots must belonging to a set. What is that field? I want to calculate actually. The underlined idea of splitting field is that. So, let us calculate the remaining roots of this polynomial. So, I can write x power 4 minus 2. So, I am going to, in other words, if you calculate all its factors, it is nothing but x square minus 2 power 1 by 2 into x square plus 2 power 1 by 2 So again, you can write this value as x minus 2 power 1 by 4 into x plus 2 power 1 by 4. And here, you can write the values as x minus 2 power 1 by 4 into I, x plus 2 power 1 by 4 into I. Please check that. So these are the four roots. 2 power 1 by 4 minus 2 power 1 by 4, 2 power 1 by 4 into I minus 2 power 1 by 4 into I. These are the four roots for this polynomial. Did you get it? Now understand that this polynomial is written product of linear factors. We accept it or not? Now see, this 2 power 1 by 4 into I is satisfying this thing. Nothing but it is satisfying this polynomial. So what is the degree of this polynomial? 2. So here we take the degree 2. Clear? Now, what is the degree of the splitting field for the given polynomial? From the hierarchy you observe? 8. That is the answer. So, always we take this hierarchy like this. So, in a small diagram, you represent like this. So, the better way to is, first you calculate all the roots of it. So, first these two roots always belonging to one extension. The remaining roots will belong to the next extension, because the coefficients obviously belong to this place. This is the next thing. So multiplying these two, you will get the degree of the splitting field. Okay for all? Any doubts in representing the thing on paper? Then I want to take the other problem also. This is also interesting for you. Just give me a moment, I will fetch a good problem for you. Just give me a moment. Now, I want to give the definition of normal extension. Please take a note of the definition. So please note down the points. Every irreducible polynomial over f that has a root in E splits into linear factors in E. Second, E is the splitting field of family of polynomials over F. Third, So I will write like this. Please take a note of these 3 points. Now I will give the definition of normal extension. Actually, if you take a field F and E is any extension of F, this is extension of F, we say that E is normal extension for F if E satisfies among the 3 conditions, one condition is sufficient. If E satisfies one condition among the 3. So if you closely look at the conditions are all equivalent. The conditions are equivalent actually. Now see, if you take a polynomial in F, it is irreducible polynomial, and I am saying that one root of f of x belonging to E, then automatically E does the thing that the remaining roots of f of x also belonging to E. So what I am saying, if you say that one root of f of x belongs to E, immediately remaining roots also belong to E. That is the property of E. What is the second thing? E is nothing but the splitting field of set of polynomials. So far what we discussed, while considering the splitting field, you are writing splitting field with respect to one polynomial. If you take the other polynomial, splitting field varies. So what it means, if you take a family of polynomials over f, let me say I have taken 10 polynomials, f1, f2, f3, f4, so on, f10. For all the 10 polynomials, E is the only splitting field, right? This is nothing but second condition. And what is third? If you take an embedding, embedding is nothing but 1-1 homomorphism. If you take an embedding sigma from E to f bar, let me say this is f bar. So everyone has a doubt what is meant by f bar. F bar is called algebraic closure of f. I will give the definition separately. F bar is also extension of f. F bar is also extension of f. So between these two, you can get an automorphism. So these two are nothing but isomorphic. So for f, you have two extensions. E is one extension, f bar is another extension. I am saying that these two are isomorphic. So if E satisfies one condition among the 3, we say that it is normal extension. So in general consideration, always we make use of condition 2. So what does it mean? If you take one polynomial over f, we say that all the polynomials, all the roots of that polynomial belonging to E. It means that E is nothing but the splitting field of that polynomial. In a simple way, in our general understanding, we can say that normal extension is nothing but the splitting field. An extension which is splitting field is called normal extension. So for our general way, we say that splitting field, normal extension, both are same. We conclude like that. Splitting field, normal extension, both are same. Okay? But the definition is given like this. But the definition is given like this. Now I will give some examples so that you can understand what is the concept of this normal extension. Okay? Can I conclude? Can I continue? Right, thank you. So after viewing the examples, you will get the idea about the normal extension. C is normal extension of R. So C stands for complex number system, R stands for the real number system, right? So if you take any polynomial over R, by default all the roots of it belonging to C, right? Because let us take a small example. I take the polynomial x square plus 4 belongings to R. Now if you write its roots, it is nothing but x plus 2a into x minus 2a. These are the factors of the polynomial. Accepted? So plus 2i minus 2i are nothing but the roots of the polynomial. These roots belonging to C. Accepted or not? So C is nothing but the splitting field of this polynomial. Not only this polynomial, you take any polynomial over R, C is nothing but the splitting field. You can define any polynomial over R, C is the splitting field. So C is nothing but the normal extension, because C is the splitting field of a family of polynomials over R. You agree or not? So this is the way we consider that C is normal extension of R. I will give one more example. I say that R is not normal extension of Q. R is not normal extension of Q. Right? Let us take the example. This example we already discussed. The example is, you take the polynomial x cube minus 2 belonging to Q of x. X cube minus 2 belonging to Q of x. So what happened? If you consider the roots of this polynomial, one root is 2 power 1 by 3, remaining root is a complex number alpha. Okay. So we have done already a hierarchy for this problem. Q of 2 power 1 by 3, Q of 2 power 1 by 3 comma I, you will get a complex root here. Accept it or not? So for this polynomial, R is not the splitting field. So in general, normal extension means you take every polynomial in the field, right? All the roots must be in this set. Then only it is called as normal extension. So here, R is not the splitting field of this polynomial. So R is not a normal extension. It is just an extension. It is not normal extension. Okay? Are you clear? Now, did you get the difference between normal extension and splitting field? If you take a set of polynomials, each and every polynomial, this set must be the splitting field. Then we call it as a normal extension. Okay? Right. Now, I want to take one more example. I think this example is given in the problem. So now you take alpha is equal to cos pi by 4 plus I sin pi by 4. Cos pi by 4 plus I sin pi by 4. And I will take the polynomial x power 4 plus 1 belongs to q of x. I say that q of alpha is normal extension of q. Q of alpha is normal extension of q. Okay. So let us prove this. Yes. Q of root is, please understand one thing. If you read the first point of the definition of normal extension, it says that if you say that I got a polynomial in Q, that polynomial possesses one root in the extension, then all the roots must be in the same extension. They should not be in the different extension. Then it will be normal extension. Please understand. Are you clear? I will give the specific idea now. Just listen. Now, this is the thing we have taken in the previous problem. Please understand that this is the polynomial I have taken in Q. Now see, if I say that this is normal extension of Q, it means that this polynomial has one root 2 power 1 by 3 in this extension. The remaining roots of this polynomial must belong to the same set, not of a different set. If all three roots belonging to this set only, this is the normal extension of this, and this is the splitting field also this. Now you got the idea? So your question is Q of root 2 normal extension of Q? Right? So here we need to understand that you consider a set of polynomials over Q for which root 2 is one root. So all the remaining roots of the polynomial, if they also belonging to the same set Q of root 2, then Q of root 2 is nothing but the normal extension of Q. Otherwise, it will just remain as a splitting field. That's all. Clear now? Are you getting the idea? Any more queries for anybody in getting the idea of normal extension? If you say that, like me, if you understand the same thing here, let me say I have taken a polynomial f of x belongs to Q. For this, alpha is a root. Now, f of x also contains remaining roots. If all the remaining roots are generated by this alpha, that means all the remaining roots will belong to the same set. So this is nothing but the normal extension of Q. By default, this is the splitting field. Okay? Does it make sense for all of you? Right. Now let us go with the problem. Still anybody has any doubts? The difference between splitting field as well as normal extension? Right. Now see, from this question, Q of alpha is normal extension of Q. This is alpha value. I have taken the polynomial x power 4 plus 1. So why? Because see, if you want to make this value as 0, x power 4 must be equal to minus 1. So x is equal to minus 1 whole power 4. Say 1 by 4. So this is nothing but, for minus 1 I will write cos pi plus I sin pi whole power 1 by 4. By the de Moivre's theorem of complex numbers, I hope this is cos pi by 4 plus I sin pi by 4. Am I correct? So this thing I have taken as alpha. Are you getting this or not? Please check everyone. If you have any other questions, we discuss. So if you consider alpha power 4 for this value, if you consider whole power 4, this is nothing but cos pi plus I sin pi is equal to minus 1. Therefore, alpha power 4 plus 1 is equal to 0 because this is nothing but minus 1 plus 1 equal to 0. So, x power 4 plus 1 has 4 roots in which alpha is a root. Now, I want to calculate what are the remaining roots for this polynomial. If I am able to say that the remaining roots also belonging to the same set, then this will become the normal extension. Are you clear? Right? Now, I will calculate the remaining roots there. So, now I consider alpha cube, alpha power 5, alpha power 7. These things I will consider. Why I have taken these things? We know that alpha power 4 is equal to minus 1. So, in order to get minus 1 in this place, I have to take the odd powers. So, alpha power 4 whole cube, if you take, you will get minus 1. Alpha power 4 whole power 5, if you take, you will get minus 1. So, alpha power 4 whole power 7 you take, you will get minus 1, I think. Right? So, alpha whole cube, if you consider, this is nothing but cos pi by 4 plus I sin pi by 4 whole cube. This is nothing but cos 3 pi by 4 plus I sin 3 pi by 4. And the value, if you consider, it is nothing but minus 1 by root 2 plus I into 1 by root 2. So if you consider alpha power 5, so this is nothing but cos pi by 4 plus I sin pi by 4 whole power 5. This is nothing but cos 5 pi by 4 plus I sin 5 pi by 4. So if you evaluate the value, it is nothing but minus 1 by root 2 minus I into 1 by root 2. Similarly, if you consider alpha power 7, this value is nothing but 1 by root 2 minus I into 1 by root 2. So, what are the roots of this polynomial x power 4 plus 1? Alpha, alpha cube, alpha power 5, alpha power 7. Why? Because alpha value is 1, alpha cube value is 1, alpha power 5 value is 1, alpha power 7 value is 1. I mean minus 1, minus 1, minus 1. If you determine that. So while considering the power, whole power 4, you will get the values as 1, minus 1. I think what I have written is alpha power 4 whole power 1 is equal to minus 1, alpha power 4 whole cube minus 1, alpha power 4 whole power 5 minus 1, alpha power 4 whole power 7 minus 1. This is my intention in writing that. So while considering the values, these are the 4 roots you will get. Now see, since the roots are nothing but multiples of alpha, all these values belonging to Q of alpha. So Q of alpha is the splitting field as well as normal extension, because you can write the given polynomial as product of linear factors in Q of alpha. Did you get the whole idea? Say. If anybody has any other questions in understanding this, you can ask. The conclusion is nothing but, let me say, I will brief the whole thing. X power 4 plus 1 is the polynomial taken over Q. For this polynomial, alpha is one root, because if you consider alpha power 4, it is nothing but minus 1. So this will get satisfied. Accepted? Now, if you want to say that Q of alpha is normal extension of Q, we have to ensure that all the 4 roots of this polynomial must belong to Q of alpha. Because this is a 4th degree polynomial, I particularly know that one root is alpha, this root belongs to this set. If I say that the remaining 3 roots are also part of the same set, then it becomes the splitting field as well as normal extension. So for this, I must know what are the remaining roots of the polynomial. It is nothing but, to satisfy here, we should get minus 1 here. Since you know alpha power 4 is equal to minus 1, in order to get the remaining roots, if you consider odd powers on both sides, you will get minus 1. So I have taken alpha power 4 whole power 3 whole power 5 whole power 7, which is nothing but minus 7, minus 1. So what are the roots? If alpha is one root, alpha cube, alpha power 5, alpha power 7 are the remaining roots. So if you particularly consider what is the exact root value, what is alpha cube, what is alpha power 5, what is alpha power 7, these are the values. The exact roots of are this. Yes, we have to write the values of these things, because we need to mention what are the remaining roots also there, right? What are the remaining roots? So here, this is one root, this is one root, this is one root. If you consider its whole power 4, this is nothing but a multiple of alpha. This is nothing but a multiple of alpha. This is nothing but a multiple of alpha. Right? So all the remaining 3 roots are nothing but multiples of alpha. Hence, they belong to the same set Q of alpha. Therefore, the splitting field is Q of alpha. Thus, it becomes the normal extension. Clear? All of you? In a simple nutshell, for this problem, I will just write 2 things, then you easily understand. So far board what I have written, this is the only thing. This is the thing I have done. So does it make sense now? Right. So any other questions for anybody? Now I want to give one definition. Later I will conclude our today's session. So in the upcoming session, I will take some of the results as well as problems. And I want to take the concept of silo theorems as well as problems based on silo theorems. There we conclude the discussion over entire abstract algebra. So I want to give the definition of algebraically closed. Take a note of that. Now see, a field K is called algebraically closed. If it has no proper algebraic extension. If it has no proper algebraic extension. Now, for this, I will give some examples that if you take the complex number system, it is a field, it is algebraically closed because you cannot find an extension which is algebraic over C. I will give the example that Q is not algebraically closed. Why? Because it has an extension Q of 2 power 1 by 3. So I got an element which is algebraic over Q. In other words, algebraically closed means you cannot find elements which are algebraic over this set. It is the actual meaning of algebraically closed. So this is algebraically closed. Q is not algebraically closed. Again, I say that this is also not algebraically closed because it has another extension Q of 2 power 1 by 3 comma I. So this is here I is the element algebraic over this. So this is not algebraically closed. This is not algebraically closed. For this you can find. Okay. Does it make sense? Yes or no? Is it clear or not? Yeah, I will say. You know the meaning of an element is algebraic, say? Yes or no? So what is meant by algebraic? So, let me see. So for better understanding, algebraically closed, let me say. Q is not algebraically closed because you can find some polynomials for which there is no root in Q. Accept it or not? Because you have taken example x square minus 2. It means that you can find an extension for Q. You can find an extension for Q such that in this extension there are some elements which are algebraic over Q. It means in this there are some elements which are roots of the polynomials over Q. It means further sets are possible in getting the extension. Okay. So C is algebraically closed because you cannot find a field which is bigger than C, such that this element is algebraic over C. Accepted now? Yeah. Now you have another word, algebraic closure. What is meant by algebraic closure? Say, this is the field F. I took an extension E. This extension, I am calling it as algebraic closure. You simply split the word, algebraic closure. So this is algebraic extension of F. So if you take any element in E, each element is root of some polynomial over F. So it means algebraic extension. Closure means you cannot extend E further. You cannot find an extension over E. This is called algebraic closure. And simply we mentioned that F bar. F bar is called algebraic closure of F. Okay? Are you clear now? Right? So based on this, I want to take a small result in the next class on this algebraic closure, because one problem is given based on the algebraic closure sets. That's the thing we have to take. So 2 power 1 by 3 comma I, it is algebraically closed, I say. Why? Because let me say, if you want to say that this is algebraically closed, you have to find a set after this so that there is an element in that set which is a root of this polynomial over this. In other words, you have to find a polynomial in this one such that at least one root is missed for that polynomial in this set. Is it possible to find? That was the question. It is possible to find. Why? Because let me say 2 power 1 by 3 comma I simply says that it contains all the roots of the polynomials. The roots may be rationals. The roots are multiples of I and multiples of 2 power 1 by 3. Am I correct? Because 2 power 1 by 3 comma I involves that it considers all the values involved in 2 power 1 by 3 I. What about 2 power 1 by 4? 2 power 1 by 5? It cannot get these values here, right? So here the extension you take it as Q of 2 power 1 by 4 comma 2 power 1 by 3 comma I. That was the extension there. Now you got it? Is it clear now or not? How we are extending the things? Yeah, that's it. So it involves cube root of two values and complex values belonging to these two, the combination of these two. Here, fourth root of 2 does not involve here. So I will take the next extension like this, fourth root of 2. Okay? That's it. So thank you very much for your cooperation. Tomorrow we will meet with the next concepts, algebraically closed. So, and I will give one suggestion for everyone that while preparing the abstract algebra concepts, I don't know how many of you have started the concept of abstract algebra preparation so far. I don't know actually. So first you go to the preparation in such a way that first you start with group theory. So you prepare the class notes or class sessions, whatever you have, and then you follow one textbook to enrich your concepts and fundamentals. then go with the previous year question papers. If you solved a set of problems in this, you are done with your preparation with regard to group theory concepts. There is no need to study each and every result, each and every problem on that, because it is very huge when compared to that. It is unlike other subjects because it will not involve any single formula. It involves multiple results. So remembering all these things is a tough task. So after finishing with group theory, you come up with ring theory and fields as well. So you prepare with the class notes, then go with the previous year questions. You solve all the possible questions, then you conclude. If you feel that there are some results useful for your preparation with the exam point of view, you prepare for those results only, not the entire book or the entire chapter. Okay? That is my suggestion from my point of view. Because I will say that if you go back with regard to group theory, almost you can forget so many things what we did in group theory. I will say. You can recollect that. If I suddenly ask a definition, what is a quotient group, how you are framing the quotient group isomorphism, you will get something confused. Even though you have learned very recently. Right? So that is the problem with abstract algebra. The best part is you can grasp the idea very easily and you can understand the result very easily. The worst thing is you easily get confused while mingling 2 or 3 results and forget the logic without having a proper revision or practice, I can say. That is the problem with abstract algebra. But compared to other questions, the length of the solution is very moderate. If you take vector calculus or differential equations, there you need to write 1-page solution. Here you need to write just half-page or more than half-page solution. That is suffice. But the thing is remembering. It will be get completed as and when Venkana sir will take the part. So mostly Venkana sir will take the sessions after this completion of abstract algebra. He want to introduce new concepts. So as per his wish, he may start with differential equations or some other part. You can straight away ask him. I think the new batch is starting from Monday onwards, right? I hope so. From Monday onwards. So he will take the sessions from Monday onwards. So for preparation, I will say that I cannot give guarantee over that Vardhaman publications. See, do you have the book right now? Or have you revisioned the context or topics in that? Say, yeah. So how many questions as per the UPSC point of view or class session point of view come from that book? How many you have the same problems what we discussed? Or does it match with the complexity of the problems what we are discussing in the class? So generally whatever the author with regard to abstract algebra, they will cover the part of group theory, the part of ring theory. Some more results based on that. They will not go to these concepts of fields, extensions, etc., etc. This is totally a different thing. It involves a lot of results. It becomes more bulky, the book. That's why they don't incorporate all the things in one single book. Because the abstract algebra syllabus is 60 to 70% is taken from the UG graduation level and the remaining 30% is taken from the PG level. That is the problem. So you cannot get a single book which covers both UG and PG as well, the syllabus. That is the problem with that. But for learning fundamentals, basic results, everything, whatever the textbook you follow with regard to abstract algebra, either S. Chand, Vardhaman publications, Joseph A. Gallian, each and everything is correct. No doubt at all. Okay? Right. So let us conclude our session right now. Thank you very much.